Hello, everyone. My name is Ao Ling Ting. I'm from Rutgers University, and today I'm going to present our work titled as Mini-Me, You Complete Me, a data-driven drone security via DNN-based approximate computing. This work is a collaboration work between Rutgers and SWIR's University of Southern California and F5 Networks. Firstly, I would like to introduce about the robotic aerial vehicles. We also say RAVs, like drones. They're a type of automatic cyber-physical systems that have been adopted in a wide range of applications, such as package delivery, urban planning, passenger transportation, and also like police purposes. This is a fast-growing market, and of course, this type of autonomous cyber-physical system are also facing different security threats, which we're going to talk about today. A typical example of RAV could be a quadcopter drone. Usually, the vehicle dynamic of a drone contains 3 axes, which we also say positions, X, Y, Z, and another 3 rotation angles, which is more about its attitudes, such as roll, pitch, yaw. In this type of drone system, the onboard controller will contain different control algorithms for navigation, for stabilizing, or for attitude changes purpose, and etc. So the most common ones are like PID controller, ETF controller, and also some other controllers like optimal control. In this slide, I will introduce RAV control model and the current threats they are facing. RAVs are typical kinds of integration of sensing, actuation, and control algorithms. The sensor components perceive the physical environment states, and the controller will carry out the system control like automatic operations, rely on the in-processor control algorithms, or we say control logics. And those calculated output values will be sent to the underlying actuators. So in this case, we say motors of the drone. For such a system, the different data-oriented attacks has been presented before against RAV systems. The first type of attack we're discussing this paper, we call external physical attack. This is more about on the sensor side. It could be a sensor spoofing attack, or it could be a GPS signal spoofing attack, or it can attack by noises or magnetic fields, but their target are the same. They try to compromise the sensing system. For the second type of attack we were discussing in this paper, as we call it internal control parameter attacks, which is focusing on attacking control parameters. Some examples could be control semantic bugs, or another type is input validation bugs. For instance, those control parameters should stay like within some secure ranges, but sometimes like if they're not defined or programmed properly, so this will give opportunity for attackers to compromise the system. For the previous defense works, there are basically 2 types of them. The first one is the state estimation base. A typical estimation detector will take the current state of the drone and pass through into state space transformation, and then to predict the next state. The current state usually include the sensor readings like accelerators, gyroscope, and the physical dynamics like its roll angle, pitch angle. The state space transformation usually is a set of equations which will be used to predict the new physical dynamics. By checking the consistency of the predicted vehicle dynamics, the detector can detect the malicious operational behaviors. In this type of work, we would like to see that the missing part might be, firstly, these works could be incomprehensive because they try to represent nonlinear factors of advanced algorithms in simple and linear templates like a PID. Secondly, is that they only emphasize on the physical dynamics and as some sensor readings, but they didn't really investigate the controller itself, which might consist blind spots in the internal control parameters of the software. Another type of related work we were discussing is that machine learning-based detectors, they usually try to extract some features out of the control algorithms. control programs. It could be some secure execution paths, or it could be trends of sensor measurement, or it could be something else like temporal behaviors. And the ultimate goal of these detectors is to train a type of classifier to classify whether the system state is a benign behavior or a malicious behavior. So it's just like a binary classifier. But in this type of work, we feel the missing part might be these. Firstly, these machine learning based detectors, they are data hanger, because a large of training data sets are needed, like to train accurate enough or like a conversion model. Secondly, is that this type of work is somehow lack of transparency, especially for the neural network model itself. In other words, like this entire control models are usually regarded as a big black box. So from all the previous insights and observations, which motivates this paper, so our question is like how can we build a better solution? The first thing we're considering that is that we need some concrete inputs and outputs for the learning model, because we cannot blindly choose the inputs and outputs. For example, like we say whatever sensor values, we just take it as inputs, and for whatever actuators, we just take it for outputs. So this is not going to work. We would like to have some concrete definitions for the inputs and outputs of the learning model to provide some transparency. And the second thing is that neural network structure. So like we know like how can we choose from so many different topologies or architectures. How can we optimize it for an embedded system like the RAV? And lastly, what type of features we would like to consider. So except for another binary classifier, can we do in a regression model? So generally, our goal is that we would like to build an explainable and lightweight neural network model to provide the safety redundancy. In this paper, our proposed method named Mini-Me contains three stages. So firstly, we reverse engineer the controller binary to get its control flow graph, and we run our data flow analysis to get a concrete definition of those inputs and outputs. So this can be so these inputs and outputs for the controller function can be used to construct a transparent learning model. And the second stage about the training, we will connect all those benign data from different like autonomous missions, and we define and train a neural network. This network will like a semantically similar approximate model compared to the original controller, and it can be used for detection purposes if we can set some proper safety thresholds. So in the last monitoring stage, these approximate learning model, we validate the perceived state outputs and alert for any abnormal operational behaviors. And we will discuss all these stages in details for following slides. Firstly, how would we identify those controller functions? Usually, we can use some like reverse engineering tools. In our case, is IDAPRO. Firstly, we extract the scripted binary out of the drill firmware and generate the control flow graph using IDAPRO. Once we have the control flow graph, we run two types of analysis. The first one is the static analysis. We set a filter using IDAPRO by checking whether a function contains arithmetical features, and such as additions or multiplications operations. So for those floating points. So this will give us a list of candidate functions. Secondly, we use some dynamic analysis to profiling the execution of the controller function and check the execution frequency of those functions in span cycles. So by doing these two types of analysis, we can identify those essential controller function within the binary. In this slide, I will give an example like how we identify the inputs and outputs for those controller functions. Firstly, we see the red parameter, that is ACCX, which means the x-axis of the accelerator. And this is an input variable because it is used to update other parameters. And the blue parameter, like ds of state px, is an output variable because its value gets changed, or we say it's being updated through this function. So it will be considered as identified output. But this is not enough, actually, because there are some intermediate, or we say temporary parameters, such as the original ones, because you can see that for this temporary parameter SPX, this parameter is firstly gets assigned, but then it gets used to update other parameters. So this is more like a temporary usage. So we will not consider this kind of intermediate variables either as inputs or outputs for our neural networks. In fact, this really helps to eliminate many unnecessary parameters to keep our model simple. In summary, like these input parameters are used to update those output parameters. So our learning model is designed to approximate this concrete control logic. And in this slide, I will give a detailed example, like how those data will look like and how we load them to train the learning model. For this kind of time series data, we take multiple time frames as inputs instead of one single data frame. For example, our predictive neural network takes the blue section, which is multiple time frame of samples, just like an image, to predict the next system state, as indicated in the orange part here. And then for the next sample, we will shift down the window and take another multiple time frames as the inputs to predict the new system states. So the benefits of this window inputs is we can improve the learning model's convergence and accuracy. In our paper, we decided to use LSTM model as the learning model for several reasons. Firstly, you can see like LSTM can train a regression model, while many other previous machine learning based works can only use for classification purpose. The secondly is that it uses a sequence of samples, not only like a single input sequence at each time. So this will help to improve our model accuracy. Lastly, because the drone system is operating autonomously, and so the data set we connected are also like in time series. So, and the LSTM models outperforms the recurrent neural network or convolutional neural network, especially when dealing with this type of time series data sets. So we choose LSTM as the learning model, and we also have more comparison to others like SVM. So you can find this in the paper. For the evaluation of our work, we set up both the physical drones and the simulators in our experiments. We discussed the physical drone like Crazy Fly, and also we consider those very popular drone simulators like Helicopter and PX4. So we test we test our design in 5 different kinds of drones in our work. In order to connect those benign running data, we will do the image show, we will schedule different path following missions for the drones. From this image, you can see that the drone will take off and follow the path to complete mission. This is a fully automatic process. So in this case, we can connect many benign training data samples. And for the controller estimation, we plot the original outputs in blue line and the estimated outputs by our learning model in the red line. So this describes the attitude changes of the drone, which is Crazy Fly. And we observed that the neural network-based approximate model generates a very close estimation results to the original ones, which means our model can predict accurately in practical flights. And another point I would like to mention is the convergence of the LSTM-based approximate model. Our goal here is to train with benign samples and minimize the error between the perceived outputs and estimated outputs. But in fact, typically given such a multi-dimensional inputs and outputs, it is not easy to determine the neural network topology and find out the best hyperparameters, because the training might not convey, might not converge or even diverge. Therefore, we employ the model tuning tool to optimize our model design, which actually guarantees the convergence and the precision of our model. In this slide, we describe how to use our training-like model to detect attacks at real time. So firstly, based on those benign testing samples, we evaluate our learning model and measure the MSE between the estimated outputs and the actual outputs. We observed that these errors are distributed in a closely normal distribution for all benign samples, which means in most conditions, the error of benign samples should stay in the range of like this mu plus minus 3 sigmas. The probability is over like 99.7% based on the property of the normal distribution. In contrast, the probability that the estimation error falls out of this interval is less than 0.03%, which is very likely happens like only when like the attacks occur. And of course, for those false positives and corner cases, we gave a detailed discussion in our paper, so you can check it for more details. In the next two slides, I will present two attack cases. Actually, we discussed 5 different attack cases in our paper, and I will pick 2 to show like how our model effectively detect them. So in the first case, we talked about the sensor spoofing attack. We assume that attacker's goal is to corrupt the local dynamic measurements, like the roll angle. So they can do this through some physical channels. This is a very actually, these measurements are very critical for the stabilizers. In our test case, so the drone will be set to the flying along a testing trajectory. We launched the sensor spoofing attack at time instance t equals 5, as you can see on the left figure. After it's taking off to disrupt the sensor readings and compromise the roll angle measurements. So this will cause failure to update the state parameters in the velocity or position controllers. So this will, crash the drone. So just as you can see on the right side figure, these like our results will or say like the real-time estimation error will show like sharp increasement, and this will break the upper boundary. So as shown as the orange line, this is generated from the benign testing estimation error distribution. Therefore, like with the protection of mini-me, the neural network-based approximate model can recognize the sudden changes of the altitude measurements and detect the sensor spoofing attack. Similarly, we discussed the control parameters attack in this case, in these slides. For real-time RAVs, any disturbance or intrusions to control parameters can cause some unsafe operations. For instance, the RAV's stabilizer logic will calculate the velocity based on the attitude error from like updated sensor measurements. So once these control parameters get messed up, and these will definitely crash or like crash the drone. So in this case, we try to compromise the control parameters in the altitude controller, which is actually a PID controller, to push one dimension of the altitude measurements to a very large scale at the time instance t equals 5, just as shown on the last figure. And our LSTM learning model successfully detects this type of sudden tempering on the control logic, because the real-time monitoring error on the right figure turns to be greater than the predetermined upper boundary. The boundary is also generated from our previous error distribution. So in this slide, we discuss about the performance overhead from two aspects. We measure the code size overhead on all 5 RAV models, which shows actually Mini-Me has an average space overhead of only 0.34%. And this is absolutely negligible for practical deployment of RAV. And note that we do not contain the offline training libraries or modules in the space overheads, since they're only used in the training, but not used in the full forecasting process once the training model gets deployed. And for the runtime ahead, the runtime ahead of all 5 RAV models is around 2.6% on average, since the Mini-Me only calculates the inference outputs, which is in our case is a real-time monitoring error. Once we have the trained model, we did not include the model training process because they are time consuming, but they can be done all at offline for Mini-Me. To summarize our work, we propose a data-driven estimation model, Mini-Me, to detect data-oriented attacks against RAVs. We utilize the data flow analysis to identify the variable changes and their mutual dependencies in RAV's controller function. We design an accurate neural network-based estimation model with lightweight and explainable topology, which can be deployed to detect against multiple types of data-oriented attacks. And our future work will be, we try to increase the model robustness in detecting stealthy attacks. And also we would like to improve the model's explainability for the root cause of attacks and their responses. And thank you very much.